Okay, so we're going to start implicit differentiation, and it's basically finding the derivative. It's just going to be a little bit different than what we already know. So we're going to build on what we already know. Up until this point, we have looked at functions defined in terms of x, like y equals x squared minus 5x, or f of x equals x squared minus 5x. And this is called the explicit form. Explicit form. Now we're going to be looking at functions where you have a relationship maybe between x squared or x and y, such as the one down here. F in terms of x and y is x squared plus 4xy minus 3y squared. This is called the implicit form. And on these situations, sometimes you're able to solve for y in terms of x, and sometimes you're not because the relationship between them are such that you cannot disconnect that relationship. So let's look at some further examples. So these are some examples of what we've done so far this semester. We have f of x equals x cubed, and we find the derivative is 3x squared. And we have sine x, derivative is cosine x. And then the next example, we have an example of chain rule, and then its derivative. And then the last one, we have quotient rule and its derivative. So my question to you is, what did we take the derivative with respect to all along this semester? What did we take the derivative with respect to? Okay, so I'm going to give you a minute to write down your answer of that. Okay, so now it turns out, what do we take the derivative with respect to? X. We took the derivative with respect to x. Every single scenario. Okay, but what if we need to take the derivative with respect to some other variable? And that is where we're going next. Okay, so let's consider the equation y equals x squared minus 5x. To find the equation of the tangent line, we would first find the derivative, and so y prime, or dy dx, equals the derivative of x squared and the derivative of minus 5x. And then we would, if we needed to find the slope of the tangent line, which is the derivative at a certain spot, we would plug in the values. But what if we rewrote the equation? What if we rewrote the equation down like here? Okay, so that's our rewritten equation. And what if we wanted to find dy dx of that? Now we already know the answer up here, right? We already know. So let's look at what it would look like if we're going to find the derivative using implicit differentiation. So the derivative of big F and with respect to x, right? So what's the derivative of x squared? The first term would be 2x. Derivative of minus 5x is minus 5. But now we come up on this minus y situation. Well, that's technically minus 1 y to the first. So we bring down our constant of 1. We bring down our power. Our new power is y to the 0. And then we need the derivative of y with respect to x equals 0. So we get 2x minus 5 minus dy dx, because all of this is a 0, not a 6, all of this becomes 1, equals 0. And then we get 2x minus 5 equals dy dx, which is the same derivative. So perhaps it's confusing on where did that dy dx come from. So let's look at that next, and that is based on the chain rule. Okay, so let's look at the chain rule when we're taking the derivative of a y term. This is really important to remember the chain rule. So if you're taking the derivative of a y term, you told me 2 slides before that we always take the derivative with respect to x, and that's true in general. So in order to find the derivative, right here, the derivative with respect to x, we first have to take the derivative with respect to y, and then multiply that by the derivative of y with respect to x. So if we have a y term like y to the fourth, if we want the derivative with respect to x of y to the fourth, we first have to take the derivative with respect to y. And the derivative of y to the fourth with respect to y would be 4y cubed. And then we multiply that by the derivative of y with respect to x. And so that is where the dy dx comes from. Another way of writing this is 4y to the third times y prime. But you have to be very careful that you know that's a y prime and not a y to the first. Going back above here again, so let's look at this again. If you notice, how does that work? Well, we first take the derivative. So if we want the derivative with respect to x, we take the derivative with respect to y, and we multiply it by the derivative of y with respect to dx. I want you to notice that when you multiply these things, this cancels out, top to bottom, and we are left with d dx. So that's how it works mathematically. Okay, so look over here on the left. I said take the derivative of y equals x to the fourth. Okay, so we have y equals x to the fourth, and we need the derivative with respect to x of both sides. Okay, so the derivative with respect to x of y. Well, remember, first, and this is 1y to the first, we have to do this chain rule over here again. So in order to find the derivative with respect to x, we first have to find the derivative with respect to y. So the derivative with respect to y would be 1y to the 0. Then we multiply that by the derivative of y with respect to x equals, and on the second one, to find the derivative with respect to x, it's just 4x cubed. So now 1y to the 0 is just 1, so we get dy dx equals 4x cubed, which we already knew that, but it's just a different way of looking at it. This slide is just kind of talking about why do we need to know how to do implicit differentiation? Why is it necessary? Well, mainly, I think what I get out of it is this last bullet point here. It's often very hard to solve for y in order to take the derivative in the normal way or the usual way. When we use the method of implicit differentiation, it eliminates that step. And if you look up here, some of these, let me highlight some. This one right here, x squared plus y squared equals 25, you could solve that for y. This one, x cubed plus y cubed equals 6xy, would be much more difficult to solve for y. So some of them we can solve for y, as you can see up above here. We have a few solved for y, but not always. It's not always possible to easily solve something for y, like the red ones. So that's why we need to know this method. And I think it's always important in math to know why you're doing something. It's not just to add more to your plate. There's a reason for it. This is an example of the equation of a circle. It's x squared plus y squared equals 25. And for this one, we can solve for y. But when we solve for y, if you look up here, we get a plus and a minus. So this is the plus radical, and this is the minus radical. So we could solve for this one separately, but taking those derivatives, honestly, are much more difficult than if we just simply used implicit differentiation. This is a picture of x cubed plus y cubed equals 6xy. And this actually has a name. It's called the folium of Descartes. And it shows an example of something that you could not explicitly solve it as a function of x, or solve for y as explicitly as a function of x. And it would be very hard to do by hand. So this is a classic example of why we need to know implicit differentiation. This slide kind of talks about the method of implicit differentiation. We kind of already went over it, but a couple things to point out for your notes is that y prime is dy dx, and the chain rule. When you're taking the derivative of a term with y in it, that's the only difference. And when you have a term with an x in it, you do it the same way you always have. But when you take the derivative of a term with y in it, when you're taking the derivative with respect to x, which is what we're always doing, you first find the derivative with respect to y, and then you multiply that by the derivative with respect to x. So these two steps are super important, and it's super important that you multiply them together. Okay, for this one, we are looking at that equation of a circle that we did before. It is x squared plus y squared equals 25. And note that this is a circle with radius 5. It says find dy dx, which remember is find the derivative y prime. It also says find the equation of the tangent to the circle x squared plus y squared equals 25 at the point 3, 4, and I already have that on my curve right here for you, 3, 4. So we have to literally find the equation of the tangent line right there. So let's get to it. In order to find the equation of the tangent line, we need to find the slope of the tangent line, which is the derivative. So we need to find the derivative with respect to x of this entire thing. That will equal the derivative with respect to x of 25. And when we're doing this, we treat it like normal unless it's a y term. So let's look at the first one. What is it, the derivative with respect to x of x squared? Well, that's just 2x. Plus, we have to take the derivative with respect to x of y squared. So we first find the derivative with respect to y, which is 2y, and then we multiply that by the derivative of y with respect to x. So we have, well, I'm going to do a reminder over here. So the derivative with respect to x is first the derivative with respect to y, and then you multiply by the derivative of y with respect to x. So that's the chain rule. We have a y involved. And now that equals, what is the derivative with respect to x of 25? The derivative of constant is 0. So now we need to solve. So we have 2y dy dx equals negative 2x. And then dy dx is negative 2x over 2y, which simplifies last step dy dx, which is also known as y prime, is negative x over y. So now we need to find the tangent line. So for the tangent line, we need our point and we need our slope. So we need the slope at the point 3, 4, and our slope is negative x over y. So our slope is negative 3/4. So our equation of our curve is y minus the y equals our slope times x minus our x value. So we have y minus 4 equals negative 3/4 x plus 9/4. 9/4 is when I multiply negative 3 times negative 3. It's a positive 9, and then it was fourths. And when we take the 4 to the other side, we have negative 3/4 x plus 9/4 plus 4. And let's simplify those fractions. We're talking about fourths. And 4 is the same as 16 fourths, because 16 divided by 4 is 4. So our final answer is y equals negative 3/4 x plus 25 fourths. Now, let's say this is an exit ticket that you're going to have to upload later. How can you check your work? Well, you can graph both of these in Desmos. That's how I got the picture. You graph x squared plus y squared equals 25, and then you can graph this tangent line and make sure that it connects where it's supposed to be, which is right over here. And if it graphs perfectly, then you know you've got the right answer. Okay, so earlier we talked about this graph, which is called the folium of Descartes, and it's a very pretty visually graph. And this one is asking you to find the equation of the tangent line at the point 3, 3. And if you can see, the point 3, 3 is already on there, and they're asking us to find this tangent line that goes through that point. And you can kind of see that that has a negative slope, so we know we're looking for a negative slope. So let's find the derivative, and we're finding the derivative with respect to x of the left side, which is x cubed plus y cubed. And we're also finding the derivative with respect to x of the right side, which is 6xy. Okay, so derivative with respect to x of x cubed is 3x squared. The derivative with respect to y is 3y squared, and chain rule dy dx. So we have the derivative with respect to y, and then the derivative of y with respect to x equals. Now this right side, you have to be very careful about this, guys. This one is the product rule, because we have 6, which is a constant, so that doesn't matter. But then we have x times y here. See it, x times y. So we are going to have to use the product rule. So the product rule is first function x times the derivative of the second function, which is y. And the derivative of y is 1, y to the 0, dy dx. So first times the derivative of the second plus the second function, y, times the derivative of x, which is just 1. Okay, so we have 3x squared plus 3y squared dy dx equals 6x dy dx, because 1y naught simplifies to 1, plus 6y. Now we're trying to solve for dy dx, so I'm going to take the dy dx term. Okay, so I'm going to take this term over here, and I'm going to take this term over here. So here's what we have. We have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. So we would factor a dy dx out, and we are left with 3y squared minus 6x equals 6y minus 3x squared. So dy dx, when we solve it, is equal to 6y minus 3x squared over 3y squared minus 6x. Okay, now we have to find the equation of the tangent line. So I'm going to go up here, tangent line. Well, what two things do we need for the tangent line? We need the point, which is 3, 3, and we need our slope, which is dy dx, evaluated at 3, 3. So we have 6 times y minus 3x squared over, I'm doing this formula down here, 3y squared minus 6 times 3. If you simplify all this mess, the numerator becomes -9, the denominator becomes +9, and your slope is -1. So your curve is y minus 3 equals -1 times x minus 3, and you get y equals -x plus 6. Sorry, we ran out of room. There's our final answer. Oh, good times. That one was really difficult and it's really long. So as you can see, these problems are really long. You're going to have to take your time. Take it slow. Okay, we're going to look at another implicit differentiation problem, and this one, I want you to note a couple things. Number one, I showed a picture up here in the top of the curve because I wanted you to see what it looked like. And then down at the bottom, we have the point 1 comma -1 that they want us to find the tangent line to. And we can see that the tangent line is going to be negative. So now we're going to find the derivative with respect to x. So the derivative with respect to x of x squared minus 3x plus 4y equals the derivative with respect to x of 0. Now, one thing to note right here, we are going to have to use the product rule. Because while 3 is just a constant, that doesn't matter at all really, or affect it, we have x times y. So we're going to have to use the product rule on that. So let's start at the beginning. The derivative with respect to x of x squared is 2x minus 3 our constant. And then we have to do the product rule. So we have first x times the derivative of the second term, which is y. So the derivative of that would be 1 dy dx. Plus the second term, y, times the derivative of the first, which is x, and the derivative of that is 1. Plus, now we have to find the derivative of 4y, and this is the chain rule. We first take the derivative with respect to y, so the derivative of 4y is 4, and then we multiply by dy dx. And that equals the derivative with respect to 0, which is 0. Okay, so I'm going to multiply through up 2x minus 3x dy dx minus 3y plus 4 dy dx equals 0. So I have to solve for dy dx, so I'm going to take a couple of terms to the right side. I'm going to take this one to the right side and this one to the right side. So I'm left with 2x minus 3y equals positive 3x dy dx minus 4 dy dx. And then I'm going to factor out a dy dx, so 2x minus 3y equals dy dx times 3x minus 4. Now we'll divide. So 2x minus 3y over 3x minus 4 equals dy dx, and that is also the same as y prime. Okay, so tangent line is what we're trying to find. On a tangent line, we need two things. We need the point, which is 1 comma -1, and we need the slope at that point. So we need dy dx, or y prime at the point 1 comma -1. So our slope is 2x minus 3y over 3x minus 4. So that becomes 5 over -1, so it is -5. So y minus our y value equals our slope, -5x minus our x value. So we get y plus 1 equals -5x, so minus, plus 5. So our final answer is y equals -5x plus 4. Okay, that's our final answer. And again, how can I check myself? Earlier, you can look at this problem and see this is such a long problem. There's a lot of room to make a mistake. So I did make a mistake earlier when I first solved this. How did I figure out I made a mistake? I graphed the original curve in Desmos. Okay, so I graphed this up here, and then I graphed my tangent line down here. And I saw that my tangent line wasn't fitting, so I went back and found my error. At first glance, this one looks really difficult, but it actually is much simpler than the last one that we did. There's two things I want you to know: that you're going to have to use product rule right here, and that we have a natural log in there and two different terms with y. Other than that, it's not a bad thing. So let's look. So we have to take the derivative with respect to x of the left side, and equals the derivative with respect to x of the right side. Okay, so we're going to have to do product rule on x times e to the x. Okay, so we have to do product rule on this one. So first times the derivative of e to the x, which is e to the x, plus the second e to the x times the derivative of x, which is 1, plus, now we have to find the derivative of natural log of y, and we need the derivative of natural log of y, which is 1 over y, and we multiply by dy dx, minus 3, and the derivative of y is 1 dy dx, that equals 0. So I have x e to the x plus e to the x. I'm going to take the dy dx terms over to the right side. So I'm going to take this over to the right side and this one over to the right side. So what I'll end up with is positive 3 dy dx, negative 1 over y dy dx. So I have x e to the x plus e to the x equals, I'm going to factor out a dy dx. I have 3 minus 1 over y. And my last step is to divide. So x e to the x plus e to the x divided by 3 minus 1 over y equals dy dx, which is y prime. And that is my final answer for this one. Doesn't look super nice, but it wasn't that bad. This one is going to be your exit ticket. I think this is exit ticket number 12 maybe. Okay, so a couple of hints. Right here, you're going to have to use chain rule and product rule. Okay, so I'm going to get you started on this. So when I find the derivative with respect to x of the left side, I first have 1 dy dx plus the derivative of cosine is negative sine, the inside alone, times the derivative of the inside, and this is where you do the product rule. So first times the derivative of the second plus the second times the derivative of the first plus 6x equals 0. Okay, I'll leave the rest of it to you. The homework consists of 11 problems found on my math lab. Pretty much all of these problems are much simpler than the ones in the examples, so take your time, text me if you need any help.